Okay, I think it's time to start. Hello, everyone. Please type yes in the chat if you can hear me well. All right, perfect. Welcome to the 119th free webinar titled Jet Pump Applications for Oil Wells, presented by our instructor, Engineer Ahmed Samir Ali. Engineer Ahmed is offshore installation manager with more than 22 years of experience in petroleum engineering and production technology. He started his career as offshore operations engineer from 2003 to 2006, and then promoted to the production department head until 2011, and then production engineering manager until 2025, and now as an offshore installation manager. Before we start our webinar, I'll just make a small presentation about OPA. Here's our next course that will be presented by the same instructor of today's webinar, Engineer Ahmed. The course titled Jet Pump Application Operations, Optimization and Design that will start in 29th November, next Saturday. You can scan this QR code to register. Don't worry if you didn't catch up to scan. I'll send all the links in the chat. Here in OPA, we have completed more than 60 courses that are now converted into recordings and available for sale in different disciplines like reservoir engineering, production technology, drilling engineering, G&G, and data analysis. You can also scan this QR code to register, or wait until I send the link on the chat. Here is also one of our website features, which is OPA App Store, when you can find affordable alternatives for software, Excel additions for specific tasks. These apps are made to resolve and save time and money. And here's one of our best services, which is mentorship. Mentorship is basically a one-to-one mentoring session. It's tailored based on the mentee's needs. You can request, explain the know-how of a software, guiding of personal data, professional guiding for PhD and master, helping undergraduate students in their projects. We have completed more than 50 mentorship programs with more than 950 learning hours. You can also scan this QR code to apply for a mentorship program. Here's our website, which is opacourses.com, where you can access everything through our website, whether you are applying for internship, mentorship, enrolling in our free webinars, applying for anything related to our services, or enrolling in our courses, whether they are live or recorded. You can access everything through our website. So make sure you pay it a visit. And finally, how to be an OPA ambassador. There are two tracks. The first one is to take one or more courses, or just take a mentorship program. So what will you get from being an OPA ambassador? You will get discounts on all courses in the future and group discounts when you invite your colleagues. Thank you for listening, and now it's time for our session. Engineer Ahmed, you can start your presentation now.
Hello, everyone. It's a pleasure to me to share knowledge through OPA Energy Academy. Thank you, Mr. Engineer Adel, for the presentation. allow me to share
Okay, you are co-host now. You can
a
share.
seminar about
Recording in progress.
in oil industry. Oil wells started
Excuse
production
me, Engineer.
as natural flow wells.
We can't see your screen. Yeah, we can see it now. All right.
Okay, again, oil well started production as natural flow wells. Or the energy down there is not able to carry out or lift the formation with, we call it, a well is ceased to flow. The well is shut in, and hence we have to equip the well with a downhole artificial lift method to pressurize or give some kind of energy to the liquid or fluid down there to be vertically lifted up, and the well is then brought back to production. So the idea of an artificial lift system or method is to lighten the fluid gradient in the tubing so that the water pressure is now able to formation fluids to the well got brought back to production. How come? By add down pressure to the produced fluids. Installing a tool equipment downhole to the liquid up to the surface with a suitable pressure enable it to flow from the wellhead or the Christmas tree or to the receiving production facilities. This way of lifting still deal with the well individually, as it has no effect on the reservoir pressure or the mechanism. It is classified under primary recovery as a second phase after the natural flow period. Again, artificial lift system, artificial lift methods, or artificially lifted up well is still the phase of primary recovery of a reservoir. But some wells start with artificial lift methods from day one of production. The well is able to flow naturally, but it might be equipped when running the completion with kind of artificial lift method or technique, either or to increase production from day one or start the process of lifting the well artificially when the well ceases to flow naturally without interrupting the production or shutting the well for workover. Among many artificial lift systems, which all may be candidate or be preferable for oil wells, we will discuss the jet pump technique, the hydraulic jet pump artificial lift system. Depending on the idea of pumping fluid from surface, يعني
Excuse me, Engineer Ahmed. We have lost your voice. Engineer Ahmed is reconnecting, so please be patient. He will back soon, inshallah. And sorry for this inconvenience. Engineer Ahmed, can you hear me well? We can see your screen now.
I'm sorry. Are you there?
Yes, I'm here.
Among all artificial lift systems, we are focusing on hydraulic jet pumping. The idea of lifting a well with a downhole jet pump is pumping power fluid from surface. The power fluid is a motive because, as we will see in details, the jet pump has no moving parts at all downhole or mechanical or electrical feed of energy. So the motive, the power is the hydraulic power of the power fluid pumped with high pressure, high rate. Either this power fluid is oil, crude oil, or filtrated water, or formation water, whatever, into the tubing, which is the conventional way of running a jet pump. The jet pump is then installed at a designated depth. We will see that this is the point where there is a communication between the tubing and the annulus, from where the produced liquids will be lifted up. The high pressure fluid will convert to high speed fluid in the jet pump nozzle, making a vacuum. This vacuum will entrain or suck, make a suction for the formation fluids to be mixed with the power fluid or the motive fluid in the mixing tube. Then this high kinetic energy for combined fluid will pass through the diffuser or venturi. So this kinetic energy will convert again to a new pressure, which will be able to lift the combined flow up through the annulus or the casing up to the surface. The candidate wells for applying jet pump technique are high deviated wells, high gas liquid ratio, and remote locations. The advantages of using jet pump are getting maximized where there are multiple jet pump wells can be powered by a central surface pump package, which means that if we can afford high pressure, high rate power fluid from a power station or power fluid station to more than one well, it will be more economic to run more than one well with one centralized surface facility, either offshore or onshore. The easy maintenance of the downhole tool after retrieving it by slick line and reinstall it in very short time. That is the main point, making jet pump the most economic, easy to maintain artificial lift system. How to retrieve the downhole pump redress it, and run it again in few hours or couple of days maximum. The jet pump has lower efficiencies than other forms of artificial systems. Okay, here we can see schematic, an easy one, explaining the idea. Here you can see the nozzle. This arrow can show us the way the power fluid, the motive, the high pressure, high rate liquid is moving through the nozzle, making the vacuum, and then from outside the nozzle, the suction flow, which is the formation fluids, will be entrained to be mixed with a mixing tube here, and then through the diffuser, the combined fluid of the power fluid and the formation fluid, we will call it combined fluid, will gain the new pressure to be lifted up from other parts to the surface. So for a typical jet pump, the operating depths might be 6,000 to 8,000 feet. The oil pour deviation could be from 0 to 8 degrees whole angle, which makes the jet pump a preferable artificial lift system for deviated wells, because there is no moving parts at all. There is nothing, no cables, no roads, nothing from surface to be mechanically moved and hence get eroded or damaged because of the deviation. It's very good or excellent for corrosion handling, good at gas handling, good at solid handling. We will see more. So the work principle of a jet pump or ejector operates on the Venturi principle, converting pressure energy of a high velocity motive fluid into kinetic energy to create suction. The suction will entrain formation fluids and then recover it back to pressure to lift the combined flow to the surface. When installing a jet pump downhole, it needs a high pressure, high flow rate pumping system on surface to afford the power or motive fluid required for jet effect in the ejector or the nozzle. The cross flow or the combined flow, as we named it, from the well will be barated for power fluid repumping to the well for continuous running for the jet pump effect in withdrawing formation fluid. Again, the pump theory is about high pressure fluid, usually water or oil, is pumping down through the motive line to the nozzle inside the jet pump. The nozzle will convert the high pressure of the motive fluid into high velocity, creating a low pressure zone at its outlet. This low pressure zone, which will be lower than the downhole pressure where the dead liquid is there, to suck it or drain it to the mixing tube. The low pressure at the throat of the pump draws formation fluid or produces the fluids into the mixing chamber. Inside the mixing chamber, the high velocity motive jet collides with the entrained formation fluid. Momentum and energy are transferred from the motive fluid to the suction fluid, resulting in a combined flow moving at intermediate velocity and pressure. What is the main components of jet pump system? According to what? According to all we have explained, the system operates continuously. The power fluid supplies energy. Jet pump converts energy to suction. Separator at surface prepares the fluid for use. Surface pump recharges the cycle. It is a closed loop or circulation operation. For power fluid at the surface, the combined flow passes through a separator which divides. Produce the fluid, oil, gas, and water from the formation sent to the processing or for sale. The power fluid get cleaned, filtrated, and recirculate back to the motive pump section. This creates a continuous circulation loop, maintaining jet pump operating as long as a motive flow is supplied. Here, we can differentiate the liquids by color. Differentiating the motive flow or power fluid from the formation entrained flow, reservoir hydrocarbons, and the production flow out the pump to surface, which is the commingled fluids or combined flow. The red is the pressurized power fluid from the tubing to the nozzle here will entrain the light blue color, which is a reservoir hydrocarbon, to be mixed in the mixing tube again. Then the commingled fluids, which is power fluid and reservoir hydrocarbon, will go in the diffuser, converts the high kinetic energy to the adequate pressure required to lift the combined flow up. It's another schematic or diagram show the same phenomena where the blue flow is the power or motive fluid, red flow the combined fluid. Here's the throat where the formation fluid entrained or suctioned, the mixing tube where combined flow has the motive energy, diffuser where kinetic energy converts to pressure to lift the fluids up. Here is the flow diagram for power motive fluid at surface. We can see this is the oil gas separator where the combined flow coming from downhole will be separated. So the production or the fluid formation fluids will go to the tanks, and then power fluid storage tank will give the high pressure plunger pump or high pressure pump the adequate rate it needs to get pressurized and then pump it again downhole. In the separation unit here, the power fluid get prepared to be pumped again, and the produced fluid will be from the top will be delivered to the processing area. What is the advantages and limitations of jet pump? Jet pump can provide effective and reliable long-term results when applied correctly to the proper well. The main point is the easily transition from natural flow to jet pump with a slim completion equipped with slide sleeve door without having to pull the well. That means what? In a natural flow well with a slim completion, tubing must be equipped with sliding sleeve door which is shut in, and there is no communication between the tubing and the annulus, as there is a permanent pucker down or below the SSD. The well then is producing naturally. Only when the SSD is open, there is a communication between the tubing and the annulus. This communication by opening the SSD does not need any pull out of the completion or any work over on the well, just slickline job to open the SSD. The same slickline unit can install the downhole jet pump. The surface facilities are there for any other well. Interconnecting piping will be there to deliver the power fluid to the tubing, and the flow line from the annulus will get the combined flow. So transaction a well from natural flow to a jet pump well does not need a workover or replacing the completion. It's only to make sure that there is permanent packer down there, which is normal, sliding sleeve door, SSD in the tubing to be opened, install the jet pump to the slick line, and start producing the oil with jet pump. No moving parts afford high tolerance to solids and manage significant volume of sand, gas, or both, as well as corrosive well fluids. The main problem in all other artificial lift systems is that there is moving parts. In Sakar Road, in ESP, even in gas lift, because gas lift has gas lift valves which have to be operated by pressure, so opening and closing the ports might cause a damage. In jet pump, as we already discussed, there is no moving parts at all. The pressure, the hydraulic, is the main motive or the motive energy, and so it can handle sand, gas, or both to some extent for sure. The low maintenance because of simple operation. Once installed, the jet pump in many cases has no downtime unless some failure might happen downhole in the seal shore equipped with seal ends to force the jet pump, the power fluid to go only through the nozzle. We will see in details the component of the downhole jet pump item by item, but it might be stay down there for a whole year if no damage or no interruption have been noticed to the seals, and the jet pump still handle the same well pressure, pumping pressure, the same rate designed for, and can lift the designated combined rate. There is no need to retrieve the pump with a slick line job. It is effective in the deviated wells or wells with severe doglegs. This pump can be used in deep offshore oil wells too. The pump is easy retrieved by rigless operation, as we discussed, eliminating great cost and downtime. It's economical in many cases. A jet pump can last the full cycle of a well. It means the whole goods that the well can deliver. When jet pump is non-applicable, the suitability for a well to jet pumping application depends on downhole inputs and also surface facilities available and matching posts. When we have not there, if we have limited surface injection pressure or power fluid supply, wells far from facilities or have facilities with limited pumping horsepower often face this limitation. That's when we don't have centralized bar fluid unit or whole pumps and extra piping to deliver the bar fluid. In cases when high gas liquid ratio, free gas entering the throat reduces jet velocity and causes flow separation, decreasing lifting efficiency dramatically. So, although the jet pump is applicable for high gas liquid ratio, it is for sure for some extent. Sand or solids above tolerance. Very high sand production erodes the nozzle. It can handle sand, but when the pump is in cavitation or the fluids got kinetic energy more than usual with sand above tolerance, there will be erosion in the nozzle or the assembly itself. This increased maintenance cost and downtime. Let's take a look on the jet pump downhole assembly item by item. There is an upper connector seal or the X-lock. This is the top coupling that locks into the tubing string slide sleeve door because the jet pump should be installed mechanically in the SSD to withstand the high pressure will be exerted above it, so it shouldn't be get moved down or get lost on the hole. The X-lock will do that for the jet pump. Via lock or profile affording seal for power fluid. So the X-lock is making two missions here. First is to install the jet pump in the slide sleeve door mechanically. The second is to afford seal to the power fluid to force it. Also allows retrieval of the pump then with slick line. It's the same way of installation. The pump itself, the housing, the carrier, the body, it's a slender body encasing nozzle, mixing section, diffuser, and connecting ports for the mixing flow after the diffuser to flow out between the seals to the annulus up to the production line. So the pump itself encasing inside the nozzle, the mixing section, the diffuser, connecting ports because the formation flow shall not be interact with the combined flow all inside the pump housing itself shall flow separately. So the pump housing often includes external slots or windows for suction from the formation fluid. The lower retainer or the seat assembly is the bottom-most coupling or retention device that locks into a lower profile seal in the tubing, so the flow from the bottom is sealed and directed only into the tubes to the throat. Here we can see schematic. The jet pump installs in the SSD. So here is the nozzle. Here is the upper seal. So the power fluid has no way, and only the nozzle here. The power fluid is coming from here, has no way but here to go and get entrained in the mixing tube. The combined flow after the diffuser has no way but here. That is the structure of the downhole jet pump to afford to pass different passes for the power fluid, the formation fluid, and the combined flow through the slots between the two seats to be lifted up in the casing. So the combination between tubing and annulus takes place between the upper and lower seal for combined flow to be produced up to the surface. Let's go to some kind of a field practice workshop where jet pump internal and external part is ordered down up, from down up, from down up. First, the bottom seal retainer, number 1, here, forms the lowest part of the jet pump assembly, providing mechanical support and housing for the packing, and aligned within the sliding sleeve door or seal bore. So the fluid from the formation has no way to flow just inside the hole in the lower retainer up to the tubing, up to the tube itself, and no fluids out of the pump can go down. The seal assembly or packing, number 2 here, installed inside the bottom seal retainer, typically consists of multiple elastomeric backing elements designed to create a pressure-tight seal between the pump and the SSD seal bore. The seal mandrel, number 3, connects to the seal assembly and extends upward into the pump body itself. The main point here is the seal element, which allows the formation fluid to come inside the pump, not from outside, and will prevent the combined flow to get down when get new pressure and go from the slots in the crossover. We will see that. The tubing spacer, connection and spacing element between the outer tube and the lower retainer or lower seal bore section. That's where the formation fluid is coming up to the next step. The crossover body, here is the point. Connecting the diffuser and the inner tube to the lower retainer or tailpipe. It has 2 groups of slots machined with different angles to afford passes for formation fluid away from the combined fluid. You can see the slots here. These are for the formation fluid for sure. And those are for the combined flow after that, and seal here will never get them combined again. The crossover has a rubber O-ring for sealing to prevent cross flow for 2 passes. The inner tube located inside the outer tube, that's for sure above the crossover, and serves as a flow conduit for the mixed production and power fluid. It houses and supports the diffuser section, where the combined flow will get the Venturi effect. The kinetic energy will be converted into pressure again for the combined flow to come out from the slots in the crossover only to through the SSD to the annulus or the casing to be lifted up. That ensures smooth transition and alignment of the produced flow from the mixing tube to the crossover body. The diffuser contained within the inner tube and connected at its low end to the crossover body. Up. We are going from down up. The mixing tube housing encases and supports the mixing tube insert, provides structural strength and alignment between the nozzle, assembly, and diffuser section. The mixing tube insert installed inside the mixing tubing housing contains to maintain jet efficiency. So the mixing tube is the point where the power fluid get mixed with the formation fluid after entrained just underneath the nozzle. The nozzle space from these slots, the power fluid is entrained and gets sucked. The nozzle spacer positioned directly on top of the mixing tube insert and serves as a connector and alignment piece between the nozzle and mixing tube. Ensure proper spacing for jet energy transfer and fluid mixing efficiency. That is the spacing between the nozzle and the mixing tube. The nozzle located immediately above the nozzle spacer and secured with the nozzle housing. The nozzle housing encloses and supports the nozzle assembly, contain an O-ring seal between the nozzle and the housing to prevent fluid bypass, typically connected to the lock mandrel, providing the mechanical linkage and sealing. Here we can see the nozzle itself and the housing mandrel. The nozzle will be here like that. If we put it upside down, that is the mandrel, the nozzle, and the nozzle housing. That is some different sizes of the jet pump. The outer tube encloses the complete inner assembly, including the nozzle spacer, the mixing tube, and the mixing tube housing, serves as the pressure containing body, isolating the power fluid from the produced fluids flow path. Connected at the upper end to the lock mandrel. Here we can see how, after assembled, the pump is ready to be running whole with the slickline tool. That is the X-lock, that is the upper part of the pump. The X-lock mandrel connects directly to the jet pump assembly, and it's used to set the pump into the sliding sleeve door, sliding side door, or pump seating nipple equipped with locking dogs that engage with a corresponding profile in the ST, securely hold the pump in position. That is the dogs. Sorry. After that, we want to recognize the K surface component. The jet pump surface system provides the power fluid, typically water, oil, or a mix, under high pressure to the downhole jet pump through the tubing. It also handles the produced fluid returning from the well. Proper understanding of surface components and operate ensure safe, efficient, and continuous production. Power fluid pump function. What's the function of the power fluid pump? It's to deliver power fluid at high pressure to drive the jet pump. Type. Usually triplex positive displacement pump for constant pressure and volume. Design parameters must match required pressure. Typically, field practice from 2000 to 4000 psi and flow rate. A surface separator. What is the function of the surface separator? To separate produced fluids, oil, gas, and water from the returned mixture. The bar fluid is often recycled after separation to reduce cost. The bar fluid tank or storage stores clean bar fluid. Why it should be clean? To maintain the surface pumping and to make sure no erosion will be there downhole with a very high pressure, high rate bar fluid might erode. Equipped with filters and strainers to prevent solids from entering the pump nozzle. Flow control and metering system, shocks, pressure gauge, and flow meters to monitor and control both injection and return lines, helps in performance evaluation and troubleshooting. That's an important point, because how could we know that the pump is there? Working, operating properly. Unless we all the time, hourly basis, can turn rate, differentiate between them. The difference is the formation gain. Routing of fluids between components. The check valves prevent backflow, protecting the pump and tanks. Control panel and instrumentation to monitor key parameters, pressure, temperature, and flow rate. Allows operators to adjust the injection condition for efficiency. That's the surface facility, surface unit component. We might have two separator. If we are dealing with downhole or formation fluid with some solids or produced gas, we might have cyclones. Here, cyclones are for solid content to be prevented, to be eliminated. High pressure pump, dumper for dumping any vibration in the system. The oil head. The return is the green line. The cycle is here. So the bar fluid system layout. The bar fluid pump, triplex plunger or positive displacement pump. Positive provides high pressure, typically pressure up to 4000 psi. Control the adjustable stroke or speed to regulate the injection rate. Suction source, bar fluid tank, cleaned and filtered. Discharge through check valves, surface manifold, tubing string. Bar fluid tank, clean tank, stores filtrated. Clean bar fluid prior to injection may include agitators, heating coils, if we are dealing with viscous crude oil, and we are going to pump it again downhole when the produced crude oil is the bar fluid. Volume size to maintain several hours of continuous operation, equipped with level gauges and overflow protection. The surface separator, product separator to receive mixture of produced fluid and bar fluid from the annulus. Perform three-phase separation, oil, water, and gas. Clean phase is either used as bar fluid or sent to production tanks. That's when we are using some of the produced crude oil as a bar fluid or produced water, the formation water. it will be economic to reuse the formation water either than inhibited or treated water, gas vented or flared as per site design if the gas will be produced. So gas facilities are there, if not, it will be flared. Equipped with pressure relief, level control and drain system, power fluid return line, the flow control, pressure gauges, flow meters, choke valves, safety and control fissures, check valves, prevent backflow into pumps, pressure relief vessel valves, protect against over pressurization, isolation valves, allow maintenance or system shutdown. The flow sequence in loop for a standalone well or flow a well in row with other jet pump wells all use the same source of power fluid and flow back to the production. So power fluid from clean tank to power fluid pump, then the tubing, downhole jet pump, the produced mixture to the separator, the clean fluid to clean tank, the production to storage or export. Factors affecting performance. What is the factors affecting the downhole jet pump performance? The erosion. The major factor affecting pump performance and life. Erosion is the gradual removal of material from the nozzle, throat, or diffuser surface due to high velocity flow of fluid mixed with abrasive particles. Improper power fluid filtration, misalignment of nozzle and throat causing turbulent and corrosive fluid environment, which accelerates material wear. That is the main problem facing the downhole jet pump, the erosion. When phase it will appear in, and you can feel it, or you can understand it when you find the enlarged nozzle and throat diameters after retrieving and disassemble the pump, giving lower differential pressure, decreasing pump efficiency and production rate, and distorted flow pattern and increased back pressure. To prevent or control erosion, use erosion-resistant material, tungsten carbide. This material of the nozzle, mixing tube, and the internal component of the pump. Tungsten carbide, stainless steel, or hardened tool steel inserts. Install surface filters. Optimize power fluid rate and pressure to reduce excessive jet velocity. Periodic inspection and replacement of nozzle throat assemblies. The second is the gas interference. When free gas enters the suction flow, it disturbs the process of momentum transfer between power fluid and formation fluid, so reducing entrainment efficiency and the pressure conversion. The gas bubble reducing the density and continuity of the suction stream, so result in unstable jet behavior. You can notice that with the unstable production from the well with the same or stable rate of injection or pumping fluid. It affects the performance as reduced suction head due to lower fluid density, decreased pump discharge pressure and flow rate. How to control the set or set the pump below the bubble point, because this problem will happen when the well get depleted, the liquid or the formation fluids are not entraining jet pump with the same rate, so gas entrance will take place. Cavitation, when the local or suction pressure drops below the vapor pressure, forming vapor bubbles that collapse violently, damaging the internal surface and destabilizing the jet. It is very related to free gas interference when happened due to reservoir flow problem. So the cavitation and gas entrance are the double face of the same coin. Causes excessive pressure drop across the nozzle or throat. Low suction pressure, high temperature, proper nozzle sizing. Here we can see the cavitation bubbles and the damage due to the fluid cavitation. Let's come to operational practice. Startup sequence. Gradually pressurize the power fluid system, filtration and fluid quality. Keep power fluid clean. Solids must be lower than 50 microns. Pressure monitoring. Maintain stable injection pressure to prevent cavitation in the downhole jet pump. Recycling and efficiency. Record the injection and production rates to assess jet pump performance. Shutdown procedure. Slowly reduce pressure before stopping the power fluid pump. Isolate the system and feed off visual pressure safely. That's field practice for sure. How to troubleshoot and to maintain the jet pump. Performance can decline due to or surface control issues. Effective troubleshooting and maintenance help sustain suitable production, extend equipment life. Let's come to some observations and try to analyze the causes and the corrective action. Drop in production rate. What happened? Erosion or wear of the nozzle throat, insufficient injection pressure maybe, and gas interference. How to correct that? Inspect surface pressure, increasing power fluid if applicable. Check for gas locking. Pull and inspect downhole pump if erosion suspected. Another observation, fluctuating in pressure and surface pressure. That may be gas breakout, cavitation, or plugging in the nozzle. So check for gas separation efficiency. Ensure adequate power fluid head. Flush or replace the nozzle. So you can flush the nozzle. If the nozzle is plugged, you may be able to unplug the nozzle by reverse circulation before thinking about pulling the pump by slick line. High separator back pressure might be, it's a surface problem. Blocking the pressure line, emulsion buildup, clean separator with lines, check valves, and control chocks. High power fluid consumption. The nozzle or throat enlargement due to erosion, incorrect jet combination. So replace worn inserts, verify proper nozzle throat ratio. Pump failed to start, flow, air trapped in lines, insufficient priming, plugged power fluid line. So please the system, check suction, ensure power fluid pump is primed. Unusual vibration, noise in surface, this is cavitation or air entrainment, check suction pressure, ensure adequate fluid level, inspect valves. Preventive maintenance practice, surface system maintenance, power fluid pumps, check lubricants, alignment, seal weekly, monitor suction, discharge pressure for early wear indication. Separators and valves, drain and clean separator internals, calibrate pressure and flow instruments periodically. The downhole system maintenance, that's another issue. Schedule periodic retrieval and inspection of the jet pump assembly. Why? Why should I retrieve the pump if it is operating efficiently and we are getting the same or the required or the designed flow rate? Because with time there might be scale accumulation and retrieval of the pump will be with more cost. Slick line might be not able to pull the pump from its place. So you have to retrieve your pump, inspect it, redress it. You might make a new design for erosion or scaling, replace worn inserts and seals, verify alignment and condition of X-lock, seating nipples and seals. Power fluid quality, that's a very important point. Use filtrated and corrosive inhibitors fluid to avoid erosion, avoid gas entrainment, check separator for performance, and suction design. Record keeping, maintain daily log of injection pressure, power fluid rate, and reduce the fluid rate. Train data to identify performance decline early. How to control and monitor the system. The control and monitor the system in a jet pump installation ensures that the power fluid circulation, downhole pressure, and production performance remain stable, safe, and efficient. Because the jet pump has no moving parts downhole, all control and optimization are done from the surface, making reliable instrumentation and monitoring essential. Maintain stable injection pressure and flow rate of the power fluid. Monitor wellhead and annulus pressure for early detection of abnormalities. Measure production rates and efficiency of the jet pump. Enable remote control and automatic shutdown in case of unstable condition. What is the control component? Surface pressure and flow controls, pressure gauge transmitters, flow meters, pressure relief valves, control valves. The metering, sure accurate measurements of power fluid and produced fluid rates. Evaluate jet pump efficiency and power fluid ratio. Support automatic control and field optimization. Provide data for troubleshooting and performance trending. What is the main metering points? Power fluid pump discharge, flow meter, and pressure transmitter that will measure injection rate and pressure of the power fluid entering the well. We need a flow meter flow, the production line, to monitor total produced fluid, oil, water, and gas. Separator inlet and outlet. Flow level and the pressure sensors to record separation efficiency and phase flow rate. Downhole pressure gauge interpretation. That's a very important point. To evaluate the downhole pump of performance with the reservoir or the downhole pressure existing, you have to attach downhole pressure gauge, memory or real time. Memory gauge with jet pump is in operation, is one of the most effective diagnostic and optimization tool in hydraulic artificial lift. The pressure data provides the drawdown the jet pump creates as a direct window into downhole hydraulics, enabling the operator to tune the jet pump to the optimum nozzle through combination and operating conditions. Data collected from the memory gauge. By the way, the memory gauge are attached to the lowest point in the pump, the lower retainer itself. It will not plug it for sure. It will be attached or hang it to it with the pump hanger or some slotted tube to let flow come through the lower retainer after get sensed and pressure measured and memorized by the memory gauge. Data collected from the memory pressure gauges will give accurate intake pressure measurements, show how much drawdown the jet pump is creating, the pressure profile monitoring, cavitation zones, flow instability or surging, optimizing power fluid rate and pressure using actual downhole pressure instead of surface values, detecting operational problems, the nozzle wear. We will see that it will give us falling in delta P and rising rate for sure, plugging or partial obstruction rising delta P and falling rate. That's a typical memory gauge graph for an onshore well installation with pressure gauge. Let's analyze it. Look. The memory gauges are attached to jet pump lower retainer. Okay. Run in hole with jet pump and gauges and set the pump in SSD. You can see that the pressure recorded is 650 psi, indicating fluid level above the pump, about 1500 feet through vertical depths of water here. That's the point where the jet pump was set. After that, started power fluid pumping, filling the tubing total head, and the pressure below the pump is about 150 psi. So the drawdown the jet pump made first is 500 psi. We can see that. Look, that is the point. That is the first trial. Here is the static pressure below the pump. After start pumping, that is the drawdown. What happened here? What happened here? Look. The power fluid pumping stopped after 8 to 10 hours, and the pressure gauges recorded the static pressure of the total tubing head, 17,000 psi here. The pump stopped. The gauges now reading the total head above the pump. Okay. Again, the power fluid pumping is resumed, and the pump could create new bottom hole pressure around 120 psi. The production took place here. The pump started again, the new drawdown. Here is a stop again, but for not much time. Start again, final stop, out of the well, pulling up. Sorry. The difference in pressure recorded is due to optimizing the wellhead pumping pressure and rate. Finally, the pump was retrieved with the gauges to download the data. Typical jet pump performance, another well. That's a failure. You can see that's a failure. After setting in the SSD, that's a failure. The failure in backing. No drawdown. The pump is not working efficiently. The another well, but here is the gauges were set in a profile below the pump before running the pump itself. Here is the trial of the pump, but it's a failure. No successful trial, non-successful trial. Here is another graph for a jet pump indicating improper combination causing gas interference. That's so. That is unstable figure. Means that there is the jet pump is not designed right. The combination is improper and causing gas interference. Another field application is performance optimization. What is the liquid foaming? The liquid foaming causing unstable flow and fluctuating downhole pressure, leading to erratic production rates, the old surface equipment, inappropriate jet pump design, mismatch between nozzle and throat sizes, and well condition, resulting in proper jet pump efficiency. We will learn how to size the right nozzle and the right throat family or size with the available data from the downhole for the reservoir. An oil field operating mainly with jet pump artificial lift system experienced a series of failure within a short period. Here is a design, that's an analysis for an oil field operating more than one jet pump. 6-month field study was conducted to investigate the relation between the production, deferment, and well shut-in hours. The study showed that the jet pump had failed more than 40 times in less than half a year, either for surface facility failure or for downhole jet pump issue. The study is for multiple wells in the same oil field with the same surface equipment characteristics. Here is the total deferred oil versus total shut-in hours. This graph wants to tell us that periodic maintenance, retrieval, plant shutdown will make less downtime for the pump. Okay. It's another graph showing us what is the main reason for downtime for the jet pump. Well intervention. That means the downhole problems will cause the well intervention to retrieve the pump, which figure 48% of oil deferred was mostly a planned deferment for production optimization, change of the jet pump combination, well testing. So designing the jet pump early from the first time will be the most effective reason for lowering the well intervention downtime because of it. Okay, again, let us evaluate the economic feasibility of jet pump installation. Why we will use jet pump versus other artificial lift systems, even when the well is candidate for the jet pump and another artificial lift system. The feasibility study is needed to determine whether the installation of jet pump artificial system is economically justified compared to other ESP or gas lift or whatever, based on capital cost, operating cost, production gains, and project payback. The capital cost, the jet pump assembly and the spare parts required, surface power fluid pumps, flow line, separators, and surface instrumentation, installation, and commissioning costs. That tell us something important, that if you have already jet pump capex, I mean pumps, flow lines, then your field is in need to more wells equipped with downhole jet pump because you already have the capex. The operational cost of OPEX, high pressure injection pump energy cost, mostly surface level maintenance by slick line, low retrieval cost, chemical treatment for foaming or scaling, which is nothing compared to the capex, and which is nothing as OPEX comparing to other artificial lift systems. Efficiency gains, reducing downtime due to no moving downhole parts, extended equipment life with proper design and monitoring. Proper design and continuous monitoring. That is efficiency. Conclusion, the jet pump system is economically feasible with proper design and control, minimize energy cost and maximize time. That's the comparison with other artificial lift system performance. The jet pump is good with moderate to low gas liquid ratio wells, while gas lift for offshore and onshore wells, deep wells, sucker rod. Yeah. Capital cost, that is the point. Relatively low to moderate. cost increase with higher horsepower required surface. For gas lift, well, gas lift equipment costs are low, but comparison cost and gas distribution system may be high. There is be high cost for power generation and cables, relatively low capital cost if electric power available. The operating cost, jet pump will be the first for sure. Some case studies for offshore and onshore wells. For onshore oil well, jet pump is more efficient and easy to apply for the space of surface facilities layout. When a standalone well is applied to jet pump system, that means in the oil field in the land or onshore, it's easy to lay out your surface facility or high pressure pump based on plunger pump. But in case of offshore, you have to run more than one more than an individual well with one single pump. The well is almost vertical, the inclination is negligible. So the case study of an onshore well, the reservoir type is sandstone, it's a depleted solution gas drive, tubing, Parker SSD X-Lock only, pump type, standard J-Person 2.75 jet pump, setting depths of the pump for sure, 3 vertical zips, perforations, flowing temperature and whatever. That is the fluid reservoir, oil gravity, water cut. You can see reservoir pressure, fluid, power fluid and production. I want to let you see that the operation and performance, that's the point, yeah. Power fluid loop, closed loop, produced water, recirculated. Maintenance frequency, 3 months. Pump change out or inspection. Typical downtime, less than 4%. Erosion sign, minor, at root, monitored. Okay. For offshore well, the jet pump is a multiple application. They are particularly efficient offshore when several wells are grouped under one central power fluid station. Instead of individual lift system for each well, a shared high-pressure power fluid system supplies multiple wells, reducing footprint, maintenance, and operating cost. Here is a sample of an offshore oil well subjected to jet pump. It's a platform, fixed jacket. Well type, oil produced, subsea tieback, or to platform. Completion, tubing, Packard retrievable jet pump insert. Jet pump, J-Person 2.75 retrievable. Setting depths, perforating depths, well orientation or deviation, status, production, under central jet pump station. Okay. This is a power fluid station. Jet pump design. Operation performance. So, centralized jet pump system will give you one shared power fluid plant for several wells, gives lower capex per well. Simple well intervention, just retrieve jet pump insert. Flexible well control via choke or injection rate adjustment, can handle solids, gas, viscous fluid from subsea tiebacks. Cost benefit to evaluate the overall economic value and operational sustainability of a jet pump installation throughout its entire service life, comparing initial cost, operating performance. Cost components were discussed as capital cost, capex, and operating cost, opex benefits. Increased production, enhanced life from depleted or low pressure wells, high daily rate, and recovery factor. So for an oil well with low productivity, jet pump is very economic here. Reliability and flexibility, moving downhole parts, so fewer failures, so lower downtime and deferred oil or deferred production. Adaptability, handle wide fluid range, sand gas, viscous Oil reduces field complexity. So life cycle, installation and commissioning, commence stop and testing 1 to 3 months only to have a surface facility valid for more than one well. Operating and optimization, steady state production, tuning injection, you may have 2 to 5 years for a well. Maintenance and overhauling the nozzle through replacement pump service annually or as needed. Replacement or upgrade, evaluate new design for better after 5 to 10 years. So a well designed and properly monitored jet pump system delivers strong economic returns and long operational life. The cost-benefit ratio improves significantly when uptime, efficiency, and maintenance are optimized through real-time control and data-driven adjustment. The future trends, digital monitoring or hybrid system will be discussed later because we can see that you can already use the jet pump in a natural flow completion well. Combination or hybrid system between jet pump and gas lift were used or experienced, but not in wide range. So the hybrid artificial system, jet pump plus ESP combination, reduced capital per well and increased life coverage. The description is hybrid completion where ESP drives power fluid for nearby jet pump wells. Jet pump with gas lift assist. Jet pump combined with annular gas injection for improving drawdown and efficiency. That extended applicability to deeper or high gas oil ratio. Last thing, that is diagram or a sketch where every item of the jet pump, name, serial number, size, when you want to get it as a spare part with the size, with the serial number, with the distance between the upper and lower seals to be suitable for the same size, same dimension SSD. That's all for now. Thank you for your time. Thank you very much.
Thank you, Engineer Ahmed, for this fruitful session. It was really beneficial. Let's take a 1 minute break until the attendees fill the feedback link, the feedback form that I have just sent in the chat, and then we will be able to receive the attendees' question. So see you in 2 minutes. Once you finish filling the feedback form, please type your question in the chat so that Engineer Ahmed could answer it. And also here is a kind reminder of our next live course. Jet Bomb Application Operations Optimization and Design that will be presented by the same instructor of today's webinar, Engineer Ahmed. The course will be conducted on Saturday, next Saturday, 29th of November. I've sent the content link in the chat so that you could review it. Okay, now it's time to receive your questions. If you want to type it in the chat, please do. Or if you want to open the mic, please raise your hand, and I will enable the mic for you to say your question. Any questions? Okay, I think there are no questions. This reflects that today's webinar, Engineer Ahmed, it was really clear and obvious. So thank you again for this fruitful webinar. And thanks to all the attendees for attending, and see you soon, inshallah, in our next webinars. Thank you.
Thank you, Adil, for giving me the opportunity to share the knowledge. I hope there will be any questions to share knowledge, to understand how our colleagues think and see the application we are talking about. But thank you for your time, Engineer, and thank you all for your time.
Thank you. It's my pleasure.